Welcome to this explainer. Today, we're diving into something truly monumental. If you've ever stood next to a modern cargo ship, the sheer, towering scale of it is literally incomprehensible. It's thousands of tons of steel shaped perfectly to slice right through the ocean. But before you get that sleek outer skin, you actually have to build the skeleton. And that brings us to a really fascinating clash of engineering and physics, forming a ship's massive steel skeleton. It is quite literally a battle of man versus metal.
So, think about this for a second. How do you actually bend the solid steel ribs of a giant ship without using any heat? It's a fantastic puzzle. If you know a bit about shipbuilding, you might know they often use fire, a technique called heat line bending, to get those complex curves for the outer hull plates. But the internal structural frames, those massive, thick bars of steel, nope, they are bent entirely cold. No torches, no heat, just pure, unadulterated brute force.
All right, to appreciate why this is such a feat, we kind of need to know what exactly we're bending. We're talking about transverse frames. Picture these as the literal ribs of the ship's skeleton. We're talking heavy structural sections, typically flat bars, offset bulb plates, or really heavy T-bars that run vertically from the keel all the way at the bottom, straight up to the upper deck. They give the hull its shape, and they take all those immense loads from the outer plating and transmit them deep into the ship's structure.
And here's the kicker. The sheer scale of the operation is just mind-boggling. A single commercial vessel doesn't just have 10 or 20 of these frames, it has hundreds of them. And because the hydrodynamic shape of a ship naturally curves and tapers from the bow all the way to the stern, practically every single one of those hundreds of ribs has a completely unique profile. Every piece of that skeleton needs to be individually shaped to match the whole perfectly. It's like a giant, heavy metal puzzle.
Okay, let's dive right into Section 1. The brute force, the hydraulic bending machine.
Let's break down the mechanics of what's happening on the shop floor. This is a method called three-point bending. First, you feed the straight steel frame into the machine, holding it firmly against two outer support points. Second, this massive central hydraulic punch descends right between those supports, just pushing straight into the steel. And third, the machine progressively feeds or indexes the frame forward. It becomes this highly rhythmic mechanical process, right? Press, release, push forward. Press, release, push forward.
Now, the magic here isn't in one giant catastrophic smash. If you tried to bend a massive steel girder 90 degrees in one go, you'd ruin it. It's all about the cumulative effect. You're applying small, incremental bends along the length of the metal. Stroke by stroke, that brute hydraulic force basically persuades the straight bar to arc. Thousands of these micro-bends eventually stack up to produce the precise, complex compound curve you need to seamlessly match the ship's outer hull.
Now you might be wondering, how on earth does the machine know exactly when to stop bending? Well, there are two main ways. The traditional old-school way is the inverse curve method. A loftsman calculates the inverse of the desired curve and literally draws a chalk line on the straight frame. The operator just bends the steel until that curved chalk line becomes perfectly straight. It's an absolutely brilliant piece of practical geometry. But in modern yards, this is mostly driven by numerical control. The 3D CAD data from the ship's digital model goes straight into the machine, translating that digital design into physical steel with absolute pinpoint accuracy.
Which brings us to Section 2, the engineer's nemesis, the physics of springback. If we zoom in on the physics of the steel itself, we find a bit of a conflict. The metal stubbornly fights back. To understand why, we have to look at two distinct properties. Steel is both plastic and elastic. Plastic deformation is what we actually want. That's the permanent shape in shape when we push the steel really hard. But steel also retains elasticity. It has this natural internal urge to snap back to its original shape. So you drive that heavy hydraulic punch into the steel, and it yields. But the very second you release that immense pressure, the elastic nature takes over, and the frame springs back just a tiny bit.
So here is the crucial point, and it's a big one. If your digital model says you need exactly a 45-degree bend, and you program your press to stop at exactly 45 degrees, you're going to fail. Why? Because when the press releases, the steel is going to sprint back to, say, 42 or 43 degrees. Hitting the exact target initially means failing the overall geometry of the skeleton. And in shipbuilding, if a frame doesn't fit flush against the hull plates, it is completely useless.
So, how do we fix it? Let's look at Section 3, the calculated victory, outsmarting the steel.
If the metal has a mind of its own, the shipbuilder basically has to outsmart it. You use the steel's own natural physics against it. Here's exactly how that works in practice.
Let's say the operator knows the ultimate goal is a 45-degree bend. Through material testing, a lot of experience, and some seriously complex computer algorithms, they know this specific piece of steel will exhibit exactly 3 degrees of springback. So they don't aim for 45, they aim for 48. They deliberately overbend the frame, pushing it right past the point of perfection.
The elegance of this whole process is best summed up right here. The operator must deliberately overbend so that when the force is released, the frame settles on exactly the correct geometry. I just find that incredibly satisfying. You aren't forcing the steel to stay at the target. You are pushing it past the target and letting its elastic retreat safely land it exactly where you need it to be. You're literally making the steel's rebellion work for you.
All right, final stretch, section 4. The skeleton is ready, moving to assembly.
So, to wrap our heads around all this, after hundreds of these frames have gone through the hydraulic press, and after thousands of calculated overbends, the skeleton is finally ready. We've taken these flat, rigid steel bars and bent them entirely cold using a 3-point hydraulic press. We completely neutralized the nemesis of springback by overbending. And now we've got our structural ribs stacked up in the shipyard, matching the CAD files perfectly, and ready for the next massive stage of assembly.
But that leaves us with a really big question to chew on. We've just mastered the art of building the ship's bones, but a skeleton isn't a ship, right? If the precise steel skeleton is finally complete, how do we build the massive flesh of the ship? How do we take all these curved ribs and flat plates and actually assemble them into those towering, multi-story blocks that dominate modern shipyards? Well, that is a massive logistical challenge, and definitely something you should be curious to explore next. Thanks for joining me on this explainer, and keep questioning how the world is built.